3.13. Consider the sequence defined by b sub n plus 1 is equal to 1 minus b sub n over 2 with b sub 0 over 0. Sorry, b sub 0 equals to 0. Okay, so this sequence is going to be different because the first question is to prove that the sequence is alternating. Okay, so all the sequence that we have seen before in these recurrence formulas are either monotonically increasing or monotonically decreasing. Okay, and then we can use that theorem that says if a sequence is monotonically increasing or decreasing, and it's bounded either above or below respectively, then it has a limit. Well, in this case, we have to prove that this sequence is not monotonically increasing or decreasing. Okay, it's alternating. It means that, you know, if I have this value at some n, the next value will be greater, and then the next one will be smaller, and something like that. Okay, so in this case, we can't use this theorem that says that the sequence has a limit because it's bounded. Okay, so then the problem kind of guides us to the strategy to prove the result. Okay, first we assume it has a limit, then we prove that the difference between the limit and the sequence is decreasing, and then we prove it finally. Okay, so let me walk you through these steps. Okay, the first part is to prove that the sequence is alternating. Okay, so then we just need to prove that this thing is true. Okay, is true. Is it smaller than 0 or what? Okay, so why does this mean that the sequence is alternating? The difference between b sub n plus 1 minus b sub n. So suppose that this difference is positive. If this difference is negative, then that's the product is going to be negative, and that means that the sequence is alternating. B sub n plus 1 is greater than b sub n, but b sub n minus 1 is actually greater than b sub n. Okay, so then you decrease to b sub n, and then you increase again to b sub n plus 1, and you could have it the other way around. Okay, that's the only possible way that you could have this product be negative. Okay, so in order to solve this, I'm going to write b sub n plus 1 and b sub n and as a function of b sub n minus 1. Okay, so b sub n plus 1 is 1 minus b sub n over 2, and we have b sub n is 1 minus b sub n minus 1 over 2. Okay, so I'm going to substitute this here. This is 1 minus b sub n minus 1 over 2, all of this over 2. So this is 1 minus 1 half, and then plus b sub n minus 1 over 4. Okay, so then let's substitute here. So this is 1 half plus b sub n minus 1 over 4 minus b sub n, and sorry, yeah, not b sub n minus 1, I have to substitute, and then b sub n is minus 1 plus b sub n minus 1 over 2, and this multiplies 1 minus b sub n minus 1 over 2 minus b sub n minus 1. Okay, so I'm going to erase this. Okay, and we have 1 half minus 1 is minus 1 half, and then you have plus 1/4 of b sub n minus 1 plus 1 half of b sub n minus 1 is 3/4 b sub n minus 1. And then here you have 1 minus 3/2 of b sub n minus 1, right? Okay, now we can kind of take, let's see, this in the same fraction. Okay, so this is, if we divide everything by 4, this is minus 2 plus 3 b sub n minus 1, and here we divide everything by 2, so this is 2 minus 3 b sub n minus 1. So we can take 1/4 and 1/2 out, so this is 1/8, that multiplies minus 2 plus 3 b sub n minus 1, and as you can see here, you can see this is minus 1 that multiplies minus 2 plus 3 times b sub n minus 1, right? Okay, so now this thing and this thing are the same, so we have a square here. Okay, this thing we can rewrite it like this. This is square, and we can erase this. Okay, So now we have 1/8, which is positive, minus 2 plus 3bn minus 1 squared, which is positive because, yeah, it's positive, and minus 1, which is negative. So we have negative. Okay, so we have just proven what they asked us. Okay, that this sequence is actually alternating. Okay, it's not growing, it's not decreasing. It's either it's growing first, then decreasing, then growing, then decreasing, and so on. Part B, assume it has a limit and find it. Okay, we have done this before, so let's call L is the limit when n goes to infinity of b sub n. So then taking limits in both sides, we have L is 1 minus L over 2. We take this to the other side, so we have 3L over 2 is equal to 1, or in other words, L is 2/3. Okay? So now C, prove that b sub n plus 1 minus L is 1/2 of the difference between b sub n minus L. Well, b sub n plus 1 is again 1 minus b sub n over 2, and then L is 2/3. Okay? 1 minus 2/3 is 1/3. Okay? And this is minus bn over 2. Now they want us to express this. We could write this like this: b sub n over 2 minus L over 2. Okay? But now, so this is kind of similar. Okay? B sub n over 2 minus b sub n over 2, and then L over 2. But L is 2/3, so 1/3 is actually L over 2. Okay? So we can take 1/2 out. So this is 1/2 of L minus b sub n. Okay? But because this is absolute value, this is the same as writing this. Okay? Because again, the absolute value of x is the same as the absolute value of minus x. Okay? So this proves the result. Okay? Okay, so then let's go to the final one. Okay, so we have proven that b sub n plus 1 minus L is equal to 1/2. The difference between the previous term in the sequence and the term and the limit. Okay. The last question is to prove that the sequence has indeed a limit. Okay. So what I'm going to argue is that this difference is the limit of this difference is going to be 0. Okay. So let's see. I have let me write b sub n minus L. Okay. So we know this is 1/2 of b sub n minus 1 minus L, right? But this one is 1/2 of b sub n minus 2 minus L, right? Or in other words, 1 over 2 squared b sub n minus 2 minus L. Well, you can make the argument again, and you will see that you have 1 over 2 cube of b sub n minus 3 minus L. And if you do this argument over and over again, you will see that you have 1 over 2 to the n over b sub 0 minus L. Okay? And actually you can prove this using induction. Okay? So b sub n minus L, you prove this, well, let us prove it by induction. Why not? Using induction. Okay? So, first of all, is this expression true for b sub 0? Okay, well, let's try. B sub 0 minus L is 1 over 2 to the 0 b sub 0 minus L, which is correct. Okay. Now assume it's true for b sub n. Now what happens with b sub n plus 1? Well, b sub n plus 1 minus L is just 1/2 over b sub n minus L. We just proved this in the previous part. And we assume this is true for b sub n minus L. So this is 1 over 2 times 1 over 2n b sub 0 minus L. And this is just 1 over 2 to the n plus 1 times b sub 0 minus L, which is the expression that we wanted to reach. Okay, so we have proven the result by induction. Okay, so we have this expression. The absolute value of b sub n minus L is 1 over 2 to the n b sub 0 minus L. Okay, if we take limits in both sides, okay, we have the limit here is the limit when this goes to infinity. Okay, this is b sub 0 minus L. B sub 0 is 0, so this is just L. But then times the limit of when n goes to infinity of 1 over 2 to the n, which is 0. Okay, so the limit between when n goes to infinity of this is b sub n minus L. So we can write this like this: the limit when n goes to infinity of b sub n is L. Okay, okay, that's what this means, and that's the end of the problem.